Okay, good afternoon. Last week we looked at what is programming and how to understand a problem and also how to understand a solution, or rather how to find a solution to the problem that we understand. So today we are going to look at a couple of things. One is how do you come up with a solution to the problem that you found last time with some sort of a computerized programming mechanism. Okay, because we are trying to find a solution from a computer point of view. Right? So this is called symbolic design. Now, symbolic design is about using symbols to come up with a solution to the problem that we found out last week, right? Because we understand computers are actually electronic gadgets, and these gadgets don't understand the language we are talking, in this case, English, right? So we need some sort of a mechanism to translate what we are saying to the computer language. Now, the computers understand only electricity, whether there is electricity or there is no electricity. So we need a mechanism to translate what we want to that electrical signal so that the computer can understand what we want. And then computer will come back with some result. And that result also we need to understand what is the computer trying to tell us. So in order to do that, we both come together into a middle ground, and that is called symbols. So we use symbols to talk and also get feedback from the computers. So before we understand how these things work, there are a couple of things we need to figure out. These are the 4 things I will be talking about today. One is computer memory. Okay. And this is where we are storing 2 things actually. Both the instructions to the computer and also the data that is needed by the computer. And then also we store the instructions, what to do with this data. Okay. So both of them are stored in the memory. This memory is, I'll show you how it looks like. So it's a bunch of boxes. Now each box has a certain thing. Let's say the first box has some instruction, second box might have some data, third box might have another instruction, and it's like that. And the processor, we call it the brain of the computer, start from the first memory location, takes that in, and then try to understand what to do. And then if it requires additional data, get that also, and then execute that instruction. And after execution, there may be some result. It requires storing, and that storing will happen. So that is the second point: fetch, decode, execute, store cycle. Third one is the language we speak, English, for example. How do you translate that into the low-level language the computer understands? There are 2 ways of doing that. One is called compiling. Other one is called interpretation. We need to figure out both of these, how they work, because the language we are going to use, Java, uses something in between here. It compiles into something, and then from there, it again gets interpreted. It uses something called a hybrid mechanism. It uses both of these in a very smart way. There are good and bad side for both. We'll see what it is. Now, to understand how a computer architecture works, right? If you go back to the history, the early days, computers were designed for single purpose. Like, for example, there is one computer designed to, say, for example, to calculate the electricity bill, right? It can only do that. And if you want to reuse that computer to, let's say, calculate the water bill, you may have to reprogram the computer. And now, in order to reprogram that, those days, you have to do a lot of wiring. A lot of wires are connected. So you have to remove some wires, plug some wires, And that's how you program the computer. So it was a very difficult task. And then this gentleman by the name von Neumann came up with a very interesting concept. He said, the computer hardware, let it be. Don't change any wiring or anything. But let's take the programming part out of the computer, or the instruction out of that controlling mechanism, and take that instruction in a memory where we can replace, change and replace. That way, you can reuse this electronic computer for multiple purposes simply by changing the program. Right? So that's how the von Neumann architecture came to the system. So in here, we have something called the central processing unit. Inside that, we have two more things, control unit and the arithmetic and logic unit, or ALU. And that is directly connected to the memory unit. So the memory unit is what stores two things, data and instructions. So by removing that from the big computer, now you can reuse the computer for various different things. So if you want to reprogram a computer, all you need to do is change the software, not the hardware. Hardware remains the same, right? Now to this, there are other two things connected, which is the input side and the output side. So input can be keyboard or a mouse or microphone, anything. Whereas the output can be speakers, screen, anything for that matter. Okay, so this is the von Neumann architecture. We need to have a clear idea about what problem the von Neumann architecture is solving. It is solving the problem of reprogramming computers, thereby removing the programming part so that we can keep changing the program and using the same hardware. Like my laptop, for example, it's the same hardware. By changing the software application, I can reuse my laptop for various different things. At one point, I'm watching a movie. Another point, I'm listening to music. Maybe some other time, I'm writing a document. So all I'm doing here is I'm changing what is in the memory unit. I'm changing the software. Hardware remains the same. Okay. And talking of this cycle, right? Talking of this cycle of getting information from the memory. So this is called fetch. Right? You start from the fetching. You fetch. RAM is a shorthand for random access memory. So the instructions are inside your memory or RAM, and you fetch one instruction to the control unit, and then the control unit try to understand that instruction. That is called decoding. And then you need to do some work with that. So you give that to the arithmetic logic unit or the ALU, which will understand the instruction and also execute the instruction. And then once that is done, we store the result inside the RAM again. And this goes on and on and on until you shut down the computer. So for example, when I turn on my laptop, what is going on? Same thing, right? So the CPU turns on and then it reads the first instruction. Where is the first instruction stored? It is stored, in this case, with my computer's case, it's actually not coming from RAM. It is coming from the ROM in the beginning when you start the computer. In the ROM, it says, okay, check your keyboard, check your mouse, check your screen, check everything. If everything is fine, then you load your operating system from the hard disk. So that initial instructions are known as the boot loader. Right? We also use the term BIOS, BIOS, Basic Input Output System. So the role of the boot or the BIOS system is to get the computer started. And then if my hard disk has, let's say, a Windows operating system, it will boot Windows operating system. If my hard disk has Linux operating system or Ubuntu, it will start the Ubuntu or Linux. If my hard disk has Apple iOS, it will start that. If my computer has Android, it will start and run. And then it goes on, right? Then it will wait for you to do something. So let's say if I start my Windows operating system, it will wait and wait till I do something there. So when I shut down my computer, then the cycle is turned off. Next time when I turn on my computer, the cycle goes on and on and on. So that's how the computer works. Okay, which brings us to the concept of programming methodologies. What are the different methods of programming, right? So there are different methods of programming. Let me also show you something before we get to that. Right, I hope you can see my screen. Computer memory is actually a bunch of boxes, right? So I can draw some boxes like this. Yeah. And now each box, let's say it starts from 0. And 1, 2, 3. Right. So it goes on like that. And the last cell is here. The last cell is N. What is N? Well, it goes from 0 to N. Anybody tell me what is N? What is the value of N? Can somebody tell me what the value of N is? Nobody talking? I said this is memory, right? So this is the entire memory we have. Now, generally speaking, we say this is RAM. So the memory has various capacities. So if I have a 1 GB, my N is 1 gigabyte. If I have 8 GB, my N is 8 GB. Okay. Now each box, by the way, holds some information. Now, for example, this box holds some information. So maybe it is holding a value, right? Say, for example, the number 100. So we can say various things about that red color box. Yeah. So it has a name. So right now I don't have a name. I can give it a name. So for example, let's say X, or let's say marks. So the name is mark, yeah, and it has a value of 100. It also has an address where the data is, right? The address is 2. Okay, and there is also a type. What type of data this is? We can say numeric or number, right? Actually, in programming, we also have different types of numbers. So we have whole numbers and numbers with decimal places. So this we say integer, a whole number, right? So I can say these 4 things about my red color box. Four things: name, value, address, and the type. Now remember, when it comes to Java, address is not used. We don't care what the address is. We let Java programming language decide in which location to store the data. So in a nutshell, this is how memory is in a computer. And you may also have, we discussed, there's another gadget, the CPU, isn't it? So the CPU has inside 2 other additional things, right? So there is a control unit, and then there is also ALU, right? So here's the control unit, and this is the arithmetic and logic unit. Together, we call this the CPU. So what happens here is every time when you start the computer, it will fetch an instruction from the first cell, right? It will fetch it. Fetch means it is reading it. And then it will try to understand what the instruction is. So that is fetching and then decoding. Decoding means understanding. After understanding, it will execute that. It will run that instruction. And maybe after that, it will store the data back. So these are the 4 things happening when it comes to computer program. Now, it's like, if I take an example, okay, so we have Taruka here, right? So if I tell Taruka, I give him some money and say, Taruka, get me a lunch packet. And Taruka will go to the canteen and buy perhaps a lunch packet. But if you break it down into this instruction set, Taruka first got the instruction from me. Instruction was, get me lunch. And since I told him in English, he understood my instructions. So that is decoding. And after he understand, he went to the canteen. So that is execution of my instruction. And then he will buy the lunch, come back and give it to me. That is storage. So then he's ready to do another instruction cycle. So in the computer, this is going on and on and on and on until you turn off the computer, right? So in a nutshell, this is how the computers work. So if you go back to the presentation, here it is. So first you start by fetching, then you decode it, then you execute it, and then you store it. Right, now in this very simple mechanism, This is how the computers work. But when it comes to humans, we have been programming computers using all kinds of different ways, right? And with all those different ways, we can identify four very distinguished, very clear methodologies. So let's look at these four methodologies and see which one are we going to learn under this unit. So since we are learning Java, we can do, in fact, more than one way of programming. We can use more than one methodology, okay, which is flexible. So the language that we are going to use, I said, is Java, right? There is a reason for that. If we go back to the history of computer programming languages, we can go all the way back to 1954, the first high-level programming language. Before 1954, there were no computer programming languages as such. There were various things, but it was not very clear as such. So in 1954, IBM came up with a language called Fortran. In fact, Fortran is a collection of two words, formula, translation. So as the name says, this is a mathematical language. It is there to translate formulas to computer programming mechanism, basically to write in English so that the computer understand the math. Okay. And it is okay because during that time, most of the computers were used for mathematical calculation, either in the military or in the government or in other places or in the education institution, in the universities for research. So it was all okay because they were all doing mathematical modeling and whatnot. But soon people realize there are more than one way to solve the problem, isn't it? There are more than one way to solve the same mathematical problem. So with that, there is no one correct way to solve the problem. There may be more than one correct way also. Now, how do you explain that to someone? Because Fortran is not very good at explaining the algorithm as to how you solve it. You have to understand the language very well in order to understand the algorithm. So in order to solve that problem, 1958 came another language by a group of people in Europe called ALGOL. That is stand for algorithmic language. ALGOL fixed one very big problem Fortran had. That was explaining the algorithm or teaching the algorithm to others. Soon people realize you can't just get a code and run. The code might run, but you may not be able to explain this to anybody. So the algol solved the problem of communication, telling people how to solve the problem. Now, if you notice carefully, apart from the Fortran line, there are two other parallel lines, one on the left, starting with a language called Lisp, and another one on the right, starting with a language called COBOL. Now, these are the three parallel paths we see in the history of programming languages. Lisp was started by another very bright young fellow from the University of the MIT University in the US. And we still use that language from 1958. We're still using it. It is heavily used for artificial intelligence processing. It's called Lisp processing language. And on the right-hand side is another very interesting thing happened at IBM. So after the World War was over, and when all the pretty much big rich universities and the government institution buying the computers and started running Fortran and Algol, they wanted to expand the sales of computers. So how can they sell more computers to the industry? In order for the industry to use the computers, they came up with another language called COBOL. COBOL stands for Common Business Oriented Language. As the name says, it is specifically designed for business purposes. Right? So those are the three parallel lines we see. Of course, there is a very small box here, interesting one in isolation called the basic language. It's not connected to anywhere. In fact, even this language is used heavily even today. It's a very nice language. You can build anything with that language. BASIC stands for Beginners All Purpose Symbolic Instruction Code. It says beginners. That means even for a beginner, it is easy to learn. And then all purpose. You can build anything with the basic language, right? People don't use it nowadays for serious application, but it's a very good language to learn programming. And if you come down with these languages, you will notice Algol becomes Simula, Simula becomes Smalltalk, and then Lisp programming has another one in between called the Logo. Very interesting language again to program graphical applications. And Algol also creates another language called Pascal, which is again a direct descendant from Algol. We've been using this language Pascal for a very long time in the universities to teach students the good practices of programming. And then COBOL has another one. These are evolution, by the way, right? PL1 or programming language 1. And then from Algol comes another one called BCPL. Then comes B language, and that becomes the C language. Very, very famous language. And then if you notice Algol path, you can see Simula coming along. Logo becomes Smalltalk. The first object-oriented language is the Smalltalk. And Simula gets enhanced with the language of C and becomes C++. And on the other side, we can see Pascal becoming Ada, and then EFL, then Object Pascal coming along with the object-oriented principles. There is also Objective-C coming up. On the left-hand side, you can see Lisp becoming Common Lisp and Close. And also there is one called Prolog, Scheme, Haskell, stuff like that. Now, left-hand side is mostly used for artificial intelligence kind of thing. Whereas on the right-hand side is used for general purpose application building. Now, if you notice, Smalltalk and C++ is becoming Java. Now, C++ is a fantastic language. In fact, if you look at most of the complex application we are using today, including your Windows operating system, the PowerPoint, the browser, everything is written using C++. It's a solid language for very complex to very simple applications. But C++ requires an expert programmer to get things done. So it may not be suitable for beginners to use C++ for serious applications. And C++ also was not ready during the internet revolution in 1995. So to solve a lot of issues C++ had, another big issue C++ had was when you, let's say you want to play a music file, you need to request from the computer, from the operating system, the memory you need for the music file. Let's say you request 5 megabyte from the operating system. And now your application is using 5 megabyte. And after you finish playing the music, you are supposed to clear that 5 megabyte, or rather give it back to the operating system so that operating system can give that memory to somebody else who's asking for memory. In C++, you have to do it explicitly, meaning you are responsible for getting memory and also giving memory, right? Now, that actually led to a lot of memory leak problems where people forgot to release the memory. The algorithm is so complex, you can't figure out whether you are given or not given, things like that. So there were issues with C++. Language is fantastic. The issues are mostly with the programmers, right? It was not very, very programmer friendly, I would say. You need to be very careful about what you're writing. But of course, like I said, C++ is used even today to write very complex programs, especially system level programs are all written using C++. So to solve all those problems came Java. Okay. Java was invented by James Gosling at a company called Sun Microsystem in 1995. And one of the things it became so popular was from day one, it was open source. And their tagline was, write once, run anywhere, which is a very, very interesting concept. Actually, Pascal had a similar concept earlier, where you write a Pascal program in, let's say, using Windows, and you can write the same, you can run the compiled code on a, let's say, on a Mac or a Ubuntu or whatever. Yeah. So Java used a similar concept, and it also got rid of some of the issues C++ had, like the memory leak problem, for example. Another issue we had with the other programming languages was they were not compatible among multiple platforms. Meaning, if I write a C program on my Windows PC, and if I take the same C program and try to run it on my smart TV, probably it might not work, because the way I store numbers is different on different platforms. Size of the numbers are different in different places. So because of that, program portability was a serious problem. And also data type was a serious problem among multiple computers. So Java solved all those issues, right? So as computer science students, we learned Java because it solved a lot of issues out there. And it is also internet ready from day one. And also it is international language, meaning all the languages you see above only support English letters. If you want to have, let's say, a message box in Sinhala or Tamil or Japanese, it is possible, but very, very difficult in other languages. Whereas in Java, natively support all the languages in the world, because while other programming languages support ASCII, Java supports something called Unicode, which has support for all the languages in the world. Now, Microsoft also wanted to come up with a great language for their platform. They could have used Java, but they wanted something faster that is running inside Microsoft boxes. So they came up with another language called C#. If you look at the syntax, they are almost the same. I would say 99% they are same, Java and C#. Few things are different here and there, but they almost look the same. Only thing changing is their infrastructure or the libraries, but other than that, everything looks the same. So this is the history of the computer programming languages, starting from 1954 to 2002. And if you notice, there are other languages that are not listed here. For example, Python is not here, right? So Python came afterwards. Then There are other older languages like PHP is not there, Rust is not there. So there are lots of other languages as well, very, I would say, specific to certain purposes. But this is like the overall high-level story of the computer programming languages. Okay, remember we talked about programming methodologies. Here's the first one. This is called procedural programming. What does that mean? Procedural programming is about taking a big project, breaking down into small chunks called procedures or functions or modules, and then you go fix one module at a time. Okay, so this is like, say, if you want to build a house, you don't build the house at once. You first build, you basically break it down into chunks. So first one probably is cleaning the land. They may be done by a different team. After the first team comes and clean the land, the second team comes to put the structure in place, and they go away. Another team will come and start building the walls. Another team will start come and fix the windows and doors. Another team will come and fix the, let's say, the roof. And finally, another team of people will come and fix the electrical things, the plumbing, the tiling, windows, doors, all that stuff. So when you break that house building into chunks like that, it becomes easy, isn't it? It becomes easy to find people, give them contracts, sign them contract, and also verification is also very easy. Same story here. When you are given a large complex project, break that down. The second one is fairly new, which we are learning under this unit, object-oriented programming. Now, procedural programming is very much or heavily based on the computer programming jargon, right? Functions and subroutines and various things. Whereas object-oriented programming, you can basically draw the physical place that you saw at your customer's location using the software pieces you are using here. You create something called objects and classes representing your customers' physical gadgets, right? On the table, perhaps documents, maybe, whatnot. So we notice, according to our previous diagram, there are so many object-oriented, fantastic object-oriented languages available today. Java is one of those. There's C++, Python, C#, Ruby, Swift. They all support object-oriented programming. Now, by the way, while these languages support object-oriented programming, they also support the previous one, procedural programming. So as the third point says, they are very useful for modeling complex systems, real-world entities, and also situations where you want to represent the interaction between different objects. And another very big one is that it supports or it promotes code reusability. What does that mean, reusability? Reusability is about writing code for one project and reusing part of that in another project. You see, that will give us more time. It saves us time because we are reusing the code. It also allows us to maintain our code. And in designing this, we use something called modular design. Okay, so because of all these fantastic features, we use object-oriented programming nowadays. Now, they're not only procedural and object-oriented. There is also a couple of others. Functional programming is another very interesting concept, right? Here, we are using mathematical functions. In fact, we go to the extent of where you don't need variables, right? Because you have a function, you calculate something and you call back, we say, go out to the parent function, right? So the parent function may have called the sub function and now it got back to the parent function. So you can pass data to the function inside and then also get data coming out of this place as well. If you look at some of the languages that support functional programming, there is Haskell, Lisp. These are, by the way, AI-based languages. But look at JavaScript. JavaScript is also a functional programming language, not Java, by the way, right? JavaScript is different to Java. So we also, under JavaScript, we have things like React, Redux, and then under Python, we have NumPy and also Swift from Apple. They all have functional programming capabilities. And the last methodology is called logical programming paradigm. What does that mean? This uses formal logic and mathematical reasoning. These days, you may have noticed we have this big ha-ho about large language models, right? Chat GPT and various things. So logical programming is used there heavily. One such language is Prolog. They are used for knowledge representation, rule-based systems, and complex logical relationships. So we looked at 4 programming principles, I mean, methodology, isn't it? We looked at procedural programming. We looked at object-oriented programming. We also looked at functional programming. And then we looked at logical programming. So these are the 4 things or 4 methodologies available for us to solve any problem we may have. Now, I'm not going to take the last 2, logical and functional. We will learn the first 2. Okay? The module approach and the object-oriented approach. That is what we are going to use. We learn with the module approach first, then we learn about the object orientation, and then we will move on with that. Because once you do object orientation, you will realize it's very, very easy. Very easy to think, very easy to do. Right. Now we learned about the computer programming language that helps us to present the problem or to basically to solve the problem. But how do you understand how to solve the problem? Or how do you communicate to someone to solve the problem? Okay. Under that, there are 2 things we can use. One is called flow charting. Other one is called pseudocode. Both are there to help us tell the other person how to solve the problem. Basically, we are communicating the algorithm to solve a certain problem. So if you look at the definition, it says flowchart is a visual representation of a process or algorithm that uses various shapes, lines, and symbols to depict the steps involved and the logical flow of the process. So it shows the logical flow, and it also shows us the steps involved in order to do this. In fact, we look at the symbol set. This is the symbol set we are using. There are more than this. There are more than this, but I think this 5 is good enough if you learn. All right, this 5 is good enough to record and document any complex algorithm. So starting with the first one, the oval shape, this is used to start the program and also to end the program. Second one is an arrow. You see, it is pointing somewhere. So the arrow is showing where it is going. So you have to follow the arrow. And the third one is a slanted rectangle. We use it for both input and output. It's called a parallelogram. Next one is a rectangle, straight rectangle. Yeah, we use that to inform process like calculation, storage of numbers, and various things. And the last one is called the decision box, a diamond, where you are getting one input, you have two outputs, but you can't have both output running at the same time. It's either left or the right. You can only have one output there. Okay, so with that knowledge, let's see how we can write some simple algorithms that we can communicate with somebody. Okay, so my first simple algorithm is how to add two numbers. Imagine you are explaining this to a child or somebody who doesn't know adding. So we say, right, start, get two numbers. So here we say enter number 1 and number 2. And then we have a, by the way, this num1, num2, sum are variables which are stored in memory. Right? And these num1, num2, sum are called variables. And if you remember the boxes that I drew, they're all somewhere there in that memory. We don't care where it is, but we know there are 3 boxes now. 3 boxes required to run this program. So we are asking, or we are getting numbers, number 1, number 2, and then we add them together, and then we store the final sum in a variable called sum. And then we display the sum, and we end the program. Very simple. You take 2 numbers, you add them and store the value in another variable, you display that variable, and you end the program. If you follow the arrow, you know where it is starting and where it is ending. So all those boxes that we saw previously are actually used here. A very simple algorithm to add 2 numbers. The other way to explain an algorithm is called pseudocode. What does that mean? A high-level, human-readable, and informal representation. It says informal, okay, of a computer program's logic. So it doesn't have specific things about the processor or the computer. It's very human-readable, English-like thing, the pseudocode. Yeah. Now, if you look at the same program that we wrote, or rather we drew previously, the flowchart, here's the same thing using pseudocode. So we have a start and the end. If you notice, between the start and the end, everything is intended to the indented. Yeah, indented. Indent, it's called indented to the right hand side. So we have enter number 1, enter number 2, sum equals number 1 plus number 2, display sum. Right? So if you look at this, it's almost the same, isn't it? This is graphical, whereas this one is not so graphical. It's very text-based. All right. So that's how you use symbols to explain an algorithm to someone. Okay. Which brings us to the next topic. What are the fundamental programming structures available out there? Meaning, what are the sort of theories that we must learn in order to become a programmers? So there are 3 only 3. Sequence, selection, repetition. That's all. If you know these 3 to do using a language, computer programming language, then you can confidently say you know almost half of the programming language, right? Because the rest is just get plugged into these three. Selection is also known as decision. Repetition is also known as loop or iteration. Now, let's look at these things in detail. Okay, we will go into the detail there. But before we go into the detail, let me also give you something called a learning path. What is a learning path? The learning path is basically a path, a road that tells you what to do first, what to do second, what to do third, and then you go on with that, and at the end, you get what you want. Right? So this is my solution, my learning path for Java for you. If you go through this path, you should be able to master the Java programming language. Number one is start with the skeleton. We also call it the boilerplate, right? That is the bare minimum to run the application. Absolute minimum to run very basic application. We call it the hello world application. Now, since we are using an IDE, in our case, we are using NetBeans. It gives us the first draft or the first boilerplate for us to get going. Same story with Eclipse or any other programming language, IDE. Okay, so boilerplate is the absolute minimum code you need to get going. You need to learn that first. Now, in that, we also learn few other tricks like code blocks. What is a code block? How do you give comments, for example, for this code block? Can I use these things for other futuristic possibilities like generating automatic code and stuff like that? So we will learn these things under number one: boilerplate, code blocks, and comments. Once you master that, go to outputting. How do I output something with Java? How do I output a number? How do I output a letter? A bunch of letters called a string. And when it comes to numbers, how do I output number with decimal places? Can I output Sinhala and Tamil? So all that comes under output. Then you need to learn about the variables in Java language. What is a variable? Where is it stored? How does it look like? What can I put there? What I can't put there, right? So they're all coming under variables. Now, along with the variables, there's also another very big lesson, the data type. What are the types of data available in Java and how to use it? How can I use it with, let's say, my variables? After you master that, you can start learning input. How do I get a user input? How do I read something from the network? How do I read something from, let's say, a disk? They're all inputs, isn't it? Then 5 is fairly simple. Now you learn the basics of computer programming. Now is a good time to run the processing. So processing is where you process your input variables, your variables as in the stuff that you got through the keyboard. Maybe you received it through network, various means. So you get the inputs and you start processing. Now, along the way, you may also do calculation. So we also need to learn how to do calculation. There is plus, plus, minus, minus. There are various ways of making calculations. So we need to learn that also. And then decision making is the next one. How do you ask a question and take a decision based on true or false? And under that list that we looked at previously, there is also loop, yeah, repetition. So how to do loop is the next question. And the last one is functional method modules. How do I get the functional module is the last one. So here is the learning path. If you go through this path, you will be able to master Java programming language. In fact, this is also same for any other language, whether it is Python, C Sharp, or whatever may be. You notice we are learning the boilerplate. We are learning how to output something. We are learning how to use variables. We learn how to get inputs, how to do processing, how to do calculations, how to make decisions, how to repeat something using loops, and then functional modules so that we can copy paste the function into another programming language. Okay, let's start with the first one out of the three, sequence. What does sequence do? It's about doing one step at a time at the correct sequence. So you start, do step one. After you do step one, you go to step two. After you do step two, you go to step three. Now, if you notice here, I use the same symbols, isn't it? From that previous chart about flowcharts. Second one is selection, meaning you ask a question. Depending on the answer, whether it is a yes or a no, you take a different route. So start, do step one, ask a question, right? And if the answer is yes, you do step two. If the answer is no, you do step three. And either way, you come back to the end. By the way, I've used yes and no. You can see here, yes means true, also means one. No means false, also means zero. If you notice this one and this one, they look the same, but there is a big difference as well here. So here you can see after doing step two, I am going back to the loop. I keep asking the question until it says no, right? So here we say step two is in a loop. Until the question becomes no, you keep on doing, keep on doing, keep on doing. Here we are putting all that together. How to make a cup of tea, right? So that's the topic, that's an output. And then in green, we do the steps. We say boil water. Oh, by the way, this is the flow chart. Here's the pseudocode for the same job. Output making a cup of tea, boil water, add tea leaves, keep the cup closed for 2 minutes, add sugar, stir well, filter it, and you serve. Right? If you look at the flow chart, it's pretty straightforward. Okay, so slide one is over. So what did we cover there? We learned about how computers work. We learned about the high-level languages. We learned about how to transmit something, how to receive something. So all that we learned. So now I guess a good time to start Java programming language. So as you can see, Java is a very popular and versatile programming language. There are a lot of jobs in the market for Java programmers. It can be used for all kinds of stuff, whether you're building enterprise level application or you're just writing a little computer game that can be run on your mobile phone. You can use Java language. Okay. And the tagline they have was write once, run anywhere. We will discuss what it means. So Java is a versatile language where you write code once and you use the compiled binary anywhere without recompiling it. That's a fantastic feature. It was created by a few people at Sun Microsystems. And in 2009, Oracle acquired Sun Microsystems. So now that's why you see Oracle Java everywhere, because Oracle bought the company Sun. Actually, they didn't buy for Java; they bought it for something else. But then Oracle now owns Java language. Now, although Oracle owns Java language, the language per se is still open. Plus, there is also other flavors of Java, OpenJDK, stuff like that. As we move forward, we will see how we can distinguish, identify what we are using, and if you want to change, how do we do that? So what do we get from Java? What are the features of Java language? Now, some of them are unique to Java, but most of them are not unique to Java. It's also common among other programming languages like C++, for example. So number one is somewhat unique to Java, compiled and interpreted. So if you look at, let's say Python, Python is always interpreted. If you take C++, it is always compiled. But Java uses both compiled and interpreted. Because of that, it becomes platform independent and portable. What do you mean by platform independent? Number three is also very, very important. From day one, Java is object-oriented. If you want, you can also use procedural programming in Java. But when you start, it's always an object-oriented language. Very rarely we go from object orientation to procedural programming. But if somebody wants to do that, no problem. That is also possible. And then next is robust and secure. What does that mean? The language is open source. It went through thousands of people to perfect it. Yeah. And because of that, it is also very robust. It doesn't break things. And if it breaks, it is not because of the language, but purely because of the user or the program. It's programmer's fault if something goes wrong. And also secure. So it's not easy to hack a Java program. Well, there are different ways. There is something called reverse engineering the bytecode and whatnot, but not very easy to do. You can always secure it further. Okay. And the next is very interesting. Distributed. What does that mean? You can write Java program and let it run on multiple computers and then start communicating with each other. That is also possible. The next is familiar, simple, and small. What does that mean? The code, if you write properly, looks beautiful, looks elegant. Remember, one of the challenges we had with computer programming languages is communication, how to tell people the algorithm or explain people the algorithm. So when you have a Java code, it becomes very easy to do. And it also gets compiled into very simple, small code, not big, large code. And the next is also very important, multi-threaded and interactive. If you want, you can write a very complex parallel processing Java program, meaning it will be running more than one thing at the same time. So that is called multi-threaded application. Interactive means you can also, by default, you will notice it's a very boring looking CLI, that is a command line interface kind of program. But you can also design beautiful icons and various things and make it interactive also if you want to. Both these things are possible with Java. And if you really optimize the language, you can have a very high performance. So in fact, most of the complex large-scale applications are written using Java language, like banking applications, insurance applications, other serious government application, military application. They all can be done using the Java language. So we can get high performance. And the last point is also very important. It is dynamic and extensible. Dynamic meaning the opposite of dynamic is static. Dynamic means at the runtime, when you're running the program, you can make changes to the program. You can load things at we call it runtime. And also extensible meaning you get basic Java, but you can start adding various components and libraries and make it do things that was not possible before. So you can expand the language. Okay, so these are the most interesting features of Java. All right, now how does it actually look like in a computer program or a computer? This is how it looks like. The Java, okay, let me go back to my paint. Clean this whole thing. Oops. So when you run, when you basically write a Java code and you compile it, you get something called a class file. Okay, you get a class file. So this class file is running inside something called a Java virtual machine. Why? Because the Java virtual machine, let me draw this first. Here's my class file or my program code, let's say. My program code, right, is running inside something called the Java virtual machine. So Java virtual machine is, as it says, is a machine. It actually simulates a computer. So your program thinks that it is having full access to a computer. So we call it a virtual machine. Now, this virtual machine is okay, it runs. One of the biggest advantages is that your Java program cannot damage the computer's memory, because your computer memory is outside the JVM. So you can't go outside the JVM using your Java program. This is why it is impossible to write viruses using Java program. You can't write viruses using Java language because it runs within the JVM and you're isolated. And in order to run my program, I might require certain library functions, right? Which is available outside of my JVM. So these are my libraries. Okay. Now this whole thing, library plus the JVM, is running inside something called Java Runtime Environment, or JRE. Okay, so this is what you need in order to run a Java program inside your machine or computer. It might be your mobile phone, it might be your smart TV, whatever. So if there's a JRE, Java Runtime Environment, available for your coffee machine, your oven, your smart TV, then you can run Java programs there. Okay, so our computers had JRE. We install JRE, the Java Runtime Environment. So when you say I am installing Java, what am I doing? I'm actually installing JRE. That's what I'm doing when I say I'm installing Java, right? So whenever or wherever there is a Java runtime environment available, you can run your Java program. Now, this is all good, but we are developers, isn't it? So in order to develop our Java program, we need certain libraries again. We need certain development tools. Okay, so they are actually sitting outside the JRE. These are called the dev tools. Now, together, dev tools and the JRE, we have something called the JDK, the Java Developer Kit. Okay, this is the entire Java environment. So we have a little Java program which is running inside the JVM. That JVM requires Java runtime environment and the libraries in order to do its job. And you are there, you're happy there. You don't need anything else. But if you want to develop Java applications, you need developer tools as well as the JDK, Java Developer Kit. So this is how the Java environment sits inside our computer. So the same thing is in another diagram here. All right. So this is the Java environment. Okay. Now we are looking at the library. In fact, we are looking at the language itself. So the Java has these keywords. Yeah, it has these keywords. Now these are called Java reserved keywords. So we have 13 per line, right? We have 13 per line into 4 lines, that is 52. There's one extra on the last line, so that makes it 53 words. So Java has only 53 words, so we call it reserved keywords. You notice we said if you want to learn a programming language, we need to learn selection and or a sequence, selection and repetition. Now you don't see those words here. Sequence, there is nothing like that. Repetition, okay, so there is a word called for and a while. Yeah, that's for repetition. And for decision making, we have a word called if, right? There is also something called else. Yeah. So apart from that, you don't see anything to output or input or anything like that, because they are all come from libraries. Okay. So what you're seeing here is the absolute minimum words from Java. Okay. So what did we do so far? We looked at the Java environment. We looked at how to solve issues by using flowchart and pseudocode. We also looked at the history of Java, how the Java is working inside our computer. It uses JVM, JRE, JDK. All these are things that we need to understand how it works. And then we are here with the Java reserved keywords. Also, if you notice, I said when you are learning a language, there is a learning path, isn't it? A learning path. Now, last week I showed you how to install NetBeans. All right. Let me start the NetBeans again. And we will look at our boilerplate code or our skeleton code now. Okay, so I hope you remember this, right? This is my hello world or my basic application. Now, we also call it a skeleton or a boilerplate application. In fact, the 14 and 15 was not there. I typed it in. But if you look at the rest of the code, now this is called the boilerplate code, right? The boilerplate code. And there are lots of different things here, which we cover in detail as we move forward. So first of all, we have a block here. Now in Java, like many other advanced programming languages, uses slash star and the star slash as a comment block. Also, if you want a single line comment, let's say I want to comment something in front of this, I use double line or double slash. This is a comment, right? That is to explain something in this line. If I want to explain for the whole block, or if I have multiple paragraphs of text, I will need slash star and a star slash. Now, I don't need this one. This is called licensing package. I have no license. Now, this is an interesting one, this code block. Okay. This is called the doc block, we call it documentation block, right? And also, if you notice, there is a bracket opening and a bracket closing. There's a bracket opening and a bracket closing. These brackets show us the starting and ending of a block. Whether it is a code or something else, it shows us an area. Okay, it shows an area. Now, if you notice this code block, actually, let me erase this as well. Now, this is the absolute minimum. We call it the boilerplate code. But I also would like to have some comments. I'll show you why. Okay. So I put /$ and I'm going to press enter now. You see, automatically I got this code block. It says author and my name. Okay, my name has an R missing. Oops. Right? So it shows my name. Now, what does this @author mean? These are called special meta characters, so symbols. These are instructions that we are giving to the IDE to do various things, especially at the time of generating our documentation. Now, if I press @, I will get all the possible things that I can use here. It says author, depreciated, hidden, parameters, C, serial, since, version, all that stuff, right? So for example, I can give a version number. I can say version 1.0, yeah, something like that. I can do the same thing for another code. Now, since you can see, I can have two code blocks, right? I have one called public class hello world, this block. Then I also have another one, public static void main code block, this one. So I can also give another comment block for this guy if I want. Okay, now it gives something else. Param ARGS. Param stands for parameters. And ARGS is the thing we are using here. So next week, when we talk about variables, you will notice what these things mean. But for now, let's see how we can generate documentation using NetBeans. I think I shared another link with you the other day. Let me see. I think I added that to the portal. Okay, so this is your LMS page. If you come down to week 1, okay, go down to the last line here. Just before week 2, there is a line, actually a resource called Code Assistance in the NetBeans IDE Java Editor. I've also given you multiple videos and links to install NetBeans. Let me click on this. It shows two things: auto code generation and creating JavaDoc with comment blocks. So it's actually a link to another site. So I'm going to click that, which will open up a website for me. And this shows code assistance, meaning there are a lot of things you can automatically generate. Okay, so we can read it leisurely. So there are smart code compiling and, code completion. Lots of things are there for you to learn here. So if you are learning a programming language, you need to master the IDE also, right? That's a must. Let me look for JavaDoc. Okay, here we go. I'm working with JavaDoc. Right. So that's what I was looking for. It says use the following features to facilitate working with JavaDoc for your code. Displaying JavaDoc, Windows or Linux, Control Shift Space. No, this is showing what is available there. This is creating JavaDoc stubs. Okay, this is what we want to do. Generating JavaDoc, right? You go to Run menu, generate JavaDoc from the menu bar. Let's try that and see. So I am going here and I am going to go to run. Generate JavaDoc is here. And by the way, before I do that, you need to make sure you have these code blocks with some documentation hints, right? Run, generate JavaDoc. And something is going on here. As you can see, it says building, scanning for projects. It is storing the information in where I created my project. Okay, building hello one JavaDoc. Right, something else is going on. 50% completed. Okay, you can see it's green. Build success. Right. Okay, so I'm going to go to the place where I had my file. So let me go to the folder here. Oops, I don't see that. Ah, here. Hello. Generated sources, notations. Okay, let me open it with a browser. So this is the generated. Actually, I didn't mention anything on the type of the documentation I wanted. Right click on the project in the projects window and choose generate JavaDoc. Okay. Let me go back. I can see I have some warnings, configuration, regenerating JavaDoc. No main description. Okay. No, I did not get the HTML. We'll have a look at that. Right. So I'll get back to you on this. So what I wanted to do today was to look at how Java is started with the skeleton or the boilerplate code, and add some comments here and try to generate a Java doc block or a documentation. Right. So next time we will go through the language further and try to understand what are the other things we can do with this language, how to get started, and then also go through the skeleton that we discussed previously. So on the skeleton, we said this is our learning path, right? So we will go through, today we went through the skeleton, then we look at how to output something, how to choose variables. Under that, we look at data types. Then we will look at how to get an input from the customer, how to do processing, how to do calculations, how to make decisions, how to use loops, and then how to create functions. Of course, after that, there are so many other things. This is the most basic, absolute basic learning path for Java. So if you can get these things organized, then the rest of the things will be easier for you.